We have the same credits, like the same classes. She's okay. Okay, just take it. I think I'll do a lot this year. I know.
They kick themselves out. They, one of them has a test that they're like, no offense, I'd rather be studying for the test. Sure, whatever. Speaking of tests, all right, hello.
Well,
Who is super sleepy?
Yeah.
Who wants to blame daylight savings time? Yes. Huh?
yeah, who wants the blames?
We can blame school too, yeah. All right. Yeah, I feel like this is the longest it's taken me to adjust to daylight savings time. Normally like 2-3 days. I'm not. All right, let's talk homework and exam. So I'm gonna open the exam tomorrow. I'm gonna get people through Monday, to get it done. And the practice exam that a lot of you have already done, I'm just gonna make that the exam. I was going to add more questions related to what we did last week, the grams and moles stuff. But I've gotten plenty of emails of like, I am stuck on the homework, please help, OMG, OMG. And with that in mind, I think it would probably be to our benefit and my benefit to just whatever the practice exam is at this moment, I'm just gonna say that's the template for the actual exam. So that's good news. And then we'll just have it open Wednesday, Thursday through Monday. So that's the plan. But that gram to mole stuff obviously isn't going to go away. I'm just gonna have it as the starting point of exam 3, okay? Which would be after spring break. Okay. So with that in mind, yeah, I had a lot of homework extension emails. I haven't gotten to most of them yet, but I've seen them. And so I'll be doing that. All right. So hopefully I've kind of reached a fair middle point here. Yeah. All right, questions, comments on that? Did everyone get my Canvas announcement yesterday? Okay, that's good news. That means it's working again. That also means, I'm gonna say this cautiously, people can message me through Canvas messages again instead of email, okay? So feel free to try that out. If you're like, I'm still sus on Canvas messages, I guess you can hit me up both ways, Canvas messages and email. But as of now, Canvas messages for me is finally working again. I've seen a few of you already try that. So that's that. All right. Yeah. Okay. I guess we'll dive in then. All right. The theme of this week, again, being in line with lab, I did some shuffling to the schedule, and we're going to be talking about collisions and heat at. Okay, that is the theme for this week. Okay, this is our heat week. We'll be learning about heat collisions, and we're going to tie it all together. All right, so some of the terminology we'll be going over the collision theory. And then after collision theory, we'll be talking about heat and then how it's measured. Yeah. We'll talk about calorimetry, which is a technique for measuring heat. And then we'll conclude this week with phase changes. Okay. The heat involved in going between solid, liquid, and gas. Okay, to melt something, you have to give it more heat, right? To vaporize something, you have to give it even more heat. All right, so we're gonna study those processes and calculate like the heat required to melt something. We're basically be calculating how much heat does it take to melt ice, you know, stuff like that. Okay. And yeah, we'll see what we get as far as calorimetry today. I think we probably will at least be able to start it. And calorimetry is what we're doing in lab this week. Okay, you're trying to figure out how much heat is released by the hot metal beads. Quick show of hands who've already done lab this week. I suspect not too many. Okay. All right. Well, perfect. Okay. So in lab, you're gonna have to measure. You're gonna have to measure how much heat is released by this metal, and then you're going to learn what the metal is based off of how much heat it releases. Okay. Basically, the idea is going to be a metal that can store more heat will be able to release more heat. Okay. Yeah, that's kind of it. All right. So we're going to talk about heat. Yeah. Next slide when you're ready. Oh, I didn't bring my model kit. Oh my gosh. Oh well, I think we'll be able to draw it out even without them. Okay. Yeah. All right. So let's talk collision theory. Okay. Collision theory is the idea that reactions occur, chemical reactions occur when two or more, but usually just two or more atoms collide with strong enough energy. Okay, that's really the simplest way of saying it, at least in my head it is. Okay. How do you get a chemical reaction? You get a chemical reaction when you have two or more atoms colliding, that means bumping to each other with strong enough energy. Okay, you can't just bump into each other. It has to have strong enough energy. So hopefully that's kind of a straightforward idea. Okay, let's say we were making water. Okay, So if you were to write out the reaction for making water, ordinarily, it'd be written out this way. Okay. And then you'll make water, H2O.
Is it just H2O? Is it O2?
Oh, I'm good. Okay, I'm getting there. Okay, but that's gonna be a minor point today. Okay, so Destiny's point is like, hey, I have a 2 there, but not there. Okay. When we learn how to balance reactions more formally, like 2 weeks from now, we'll address that further. If you buy hydrogen gas in a cylinder, it's H2 hydrogen gas. Okay, if you buy oxygen gas in a cylinder, heck, the oxygen you're breathing right now is O2 gas. But water's chemical formula is H2O. Okay, when we drew water's Lewis structure, it feels like that, if we remember, and that's going to be on the exam that opens tomorrow. Okay. And when we drew Lewis structures for those 2 molecules 1 or 2 weeks ago, that's what we did. Actually, I think we can easily finish the point you had started to make. Okay. If water comes in a package of 2 hydrogens and 1 oxygen, are we not going to have a leftover oxygen? See that? Okay. We went, if we started labeling stuff like 1, 2, 1, 2, and then for oxygen, we go 1, 2. If we used this to make the first water, hopefully we're in agreement that there's 1 oxygen that didn't get to see any action. Okay. What if we also wanted to make water with this other lonely oxygen? What would we need? 2 more hydrogens, okay? Let's build another 2 hydrogens. Hydrogen number 3, hydrogen number 4. Now we can build another water molecule. Okay, finish your drawings. Okay. What do you think? Are there any leftover unreacted atoms? Maybe, maybe not. I don't see any either. Yeah. There's no leftover unused atoms. We've made the maximum amount of water possible. Okay. When there's no leftovers, this is called a balanced equation. Okay. This is a balanced equation. And that's a sneak preview for 2 weeks from now. Okay, we're going to be balancing equations day and night for like 2 straight weeks. All right. But this is a little preview. Okay. Now, in order to turn our balanced equation from pictures to written form, you just have to count how much you have of each. Okay? How many water molecules did we make?
2.
So check this out. There. How many oxygen molecules did we use on the left side of the reaction before any reaction? How many oxygen molecules? 1 O2 molecule. Okay, so you can put a 1 there. Eventually, you want to get in the habit of just not writing a 1, because in chemistry we're lazy about 1s. If you wrote a 1, I wouldn't care. I'm not nitpicky like that. And then how many hydrogens molecules? Okay, that's atoms. Okay, that's good, but they come in packages of 2. There we go. Okay. So that's how you would write a balanced equation. That's our first balanced equation this semester. Great question, Destiny. I didn't plan that, but I didn't want your brain to be bugged by an unbalanced equation for the remainder of class and then not pay attention to the main thing. I hate it when that happens. So we'll get that done. Okay. All right, so that's the balanced equation. Most things I'm going to show today are going to be automatically balanced. So we're not going to worry too much about making sure everything's balanced. The thing that I want us to care more about today is the movement of the atoms. Are they pointing the right way? Are they moving fast enough? Are things crowded? Are things less crowded? More crowded might mean more collisions, okay? Chemistry is a collision science. You need things to crash into each other, okay, in order to make things happen, okay? All right. Yeah. Boom. Now the A flat. Yeah, I have perfect pitch. That's a B. One of my random talents. I don't know what's good for you. You online, let me just make sure chat's open. Okay, great. So collision theory, reactions occur when you have 2 or more atoms colliding with strong enough energy. So what I'm going to do, let's take a break from writing notes. And I'm going to load up a tool on the screen that'll kind of help us visualize the movement of atoms. Okay. For those on the internets, okay, if you were to scroll down to week 8, all right, you'll see this collisions simulator website to play around with from the University of Colorado. Okay, so that's what I'm going to be using here. Okay. All right, and you click it, and you're going to be like, huh? We're talking about collision theory. Why is it a module called gas properties? When you study gases, it will teach a lot of very similar ideas about collisions, okay? We will revisit gases more formally as a topic of study 4 or 5 weeks from now. But by studying collisions right now, you'll get familiar with a lot of gas concepts as well, okay? There's other things you can play with, okay? But we're just going to click this ideal gas module. What does ideal mean? I'll define that another day, okay? Now, when you first play with this thing, you're like, oh, there's so many options. What do I do? What you want to do is there's 2 types of atom. Big, small, okay? So let's start with big, the blue ones, okay? And we're going to open this lever and push some gas into there. Yay, okay? And there they go, okay? If that's painfully slow, we can speed things up, okay? So that's just the question. How can we speed things up? Okay, here's some things we can play with. We can add some heat, or we can cool it down. We can make this container smaller or bigger, okay? So that's the question. I'm gonna have you think about for a little while. Okay, how can we make things collide into each other more? Okay, it doesn't have to necessarily be faster. Faster can probably help with more collisions, but how do we get things to collide more? Okay, while you think on that, I'm going to pump in some of the smaller gas, okay, the smaller red dots. Once I pump those in, I want you to see whether the smaller atoms are moving at the same speed as the blue, or a faster speed, or a slower speed. Here we go. Here we go. Should I zoom in more? Maybe. Red is way faster. Okay. Let me give an analogy, okay, about that. In order to make a hole in this wall, okay, I would talk about baseball, right? I was voluntold to be a baseball coach yesterday, so I guess I'm coaching baseball this year again. Okay. So if I were to want to bust a hole in this wall, I gotta throw that baseball pretty fast, okay, in order to bust a hole. Otherwise, it's just gonna bounce off. Now, bowling ball comparison. To make a hole in the wall, can I get away with a lower speed? Okay, I sure can. Lower speed, okay, I'll probably still make that hole in the wall. Said another way, if I threw the bowling ball with the same speed as the baseball, it would have a higher energy. There would be more damage, okay? So here's an equivalent way of thinking about it. The bigger the object, the less speed required to get to an equal amount of energy, okay? Fast baseball versus slow bowling ball, in other words, is the same amount of energy, okay? So how does this relate to atoms and temperature? At a given temperature, you are moving things into motion, okay? As you heat things up, the smaller atoms, by virtue of being lighter, naturally will move more, even though it's the same temperature. Because it's the same energy, just smaller things move more easily. That's kind of the main idea here. Okay, good. All right, now I gave you some ideas of things we could play with, okay? We could play with the temperature or we can play with the volume, okay? What do you think? Which one should we play with first? Just vote, it doesn't matter. Temperature, yeah, okay. So, shall we burn it up? Cool it down? Burn it up, okay? So make your prediction of the movement. We're adding heat to the system. And then look at the pressure gauge. Is that 14 right now? Look at that thermometer go nutso, okay? And look at the atoms go nutso, all right? Higher temperature means more movement. Do we have more collisions, less collisions? More, okay, swell. All right, now let's play with container size. I'm gonna make the container bigger. Okay. Predict what happens with the number of collisions. All right, here we go. And you saw the pressure went down because pressure is the strength of collisions, the number and strength of collisions on the sensor, okay? Pounds, pressure is measured like pounds per square inch, for example, okay? Pound per square inch, so on a square inch, how much force are you applying? That's pressure. So notice the pressure went down as I expanded, all right? Maybe it helped to show you the opposite effect. I'm going to confine this. Okay, the pressure quadrupled. As I went to a quarter of the space, the pressure quadrupled. Exactly, okay? When we study gases, we're gonna see that mathematics apply. If you quarter the volume, you get 4 times the pressure, all else equal. If you do 10 times the volume, you'll have 1/10 the pressure. There's that inverse relationship, okay? Don't worry so much about the math right now. All I care for you to notice right now is I shrunk the space and now they're bumping into each other like crazy, okay? Like a Walmart on Black Friday, right? Okay, Walmart Sunday morning, Black Friday, right? So, I think that's enough of that. You can play around, you can change the lightness and heaviness of particles. Yada, yada, yada. All right. So let's write down our findings here. Okay. No fancy math equations. Okay. That's for your Chem 111 students. Okay. And for those going on, it's not as bad as it sounds. Okay. So I want us to keep track of how we got more collisions. So let's first talk about, people want to talk about temperature first. We got more collisions from higher or lower temperature? Good. All right. How about the volume? Oh, you're all still braiding. Okay. Do volume next. How did we get things to collide? Increase the space or shrink the space? Shrink, okay, down. I know the temptation is to say more of something means more of something else, but that's not true for all things in life. Okay, more space, less collisions. It's like that's why in small towns you see the same people all the time, right? Less space. People hate small talk, they try to move to a bigger town, right? But then you just collide with more strangers. Anyway, side talk. Pressure, okay? More pressure means yes, okay? How about amount of particles? If we have more particles, do we have more collisions? Yeah, okay. So everything is up except for volume. Okay, everything is up except for volume. And when we study gases, the amount of particles will get a symbol of a lowercase n. Okay. Yep. And that's how you control collisions. Okay. One of the most important factors here, though, in my mind, temperature is probably the most important of these 4 variables. Okay. Temperature does 2 things. Okay. Temperature gives more collisions, but it also gives stronger collisions. Okay. And if you have trouble making a chemical reaction happen, you often turn up the temperature. Okay. You're going to get more collisions and you're also going to get stronger collisions. All right. Some bonds are really resistant to break. You have to give them a really hard punch. Okay. Sorry to be a little violent. Okay. Chemistry is a little violent. All right. You have to whack that molecule really hard to break the old bond and make the new bond. Okay. So you need stronger collisions. Okay. Jacking up the temperature versus these other variables is the method of getting stronger collisions. Okay. You can write this down. Helps break bonds. Okay, especially strong bonds. Stronger the bond, the higher the temperature you're usually going to need. Okay. Okay. So that's kind of a part 1 of collision theory of needing more collisions. Okay. There is a part 2 we haven't written yet. Okay. I didn't want to overwhelm you. Okay. Well, hopefully it makes sense. You need more collisions for something to happen to increase the likelihood, the probability. Okay. You can apply statistics to all this, but I think that would make everyone run away. So we're not going to go there. Okay. But there's a part 2 to collision theory. Okay. Reactions occur when 2 or more atoms collide with strong enough energy. Okay. And there's an end. The correct alignment. Okay. Or some people use the word orientation. Orientation, alignment, they got to be facing each other the right way. Okay, things have to be aligned. Okay. And as I show you some examples, I think it'll make sense and it'll feel kind of common sense-ish, but it's something often we kind of just take for granted. Okay. In order for a reaction to happen, things have to be lined up the right way. Okay. We can't make water if the hydrogen and oxygen aren't hitting each other. Okay. They have to hit each other. Okay. You have to have the correct bonds aligned in order to make stuff happen. Correct atoms. Okay. So that's part 2. You need strong enough energy, okay, and the correct alignment. And of course, more collisions, easier reactions. Okay. So let's talk alignment. I have a few example reactions. Okay, so I'll call this slide examples of correct versus incorrect alignment. Okay. Well, it's not like incorrect. It's not, we're good / bad. I think that's better. You can't call nature incorrect. Nature's nature. Good / bad. I think that's better. Okay, so let's draw some reactions. Let's do example number 1. What I want us to do, here's the reaction as written. We're going to take HCl and we're going to react it with fluorine. Okay. Now, fluorine normally exists as a diatomic like F2, just like we have O2 and H2, but we're just going to ignore that for simplicity's sake. At the end of the reaction, we want to end up with an HF and a Cl. Okay, we want to have a replacement going on. We want H to end up with F instead of Cl. All right, 2 weeks from now, we'll call this a single replacement reaction because one thing ends up getting replaced, but you don't have to worry about that. So let me draw some possible drawings here, unless you want to come up with your own. Okay, there's one possible orientation. All right. We can say, hey, what if the fluorine is coming towards that chlorine? Okay. Or maybe they're both approaching each other. It doesn't really matter. But let's say the fluorine is approaching the HCl on the chlorine side. Will that get us to end up with an HF and a Cl by itself? All right, you felt that already. I love it. That's all there is to collision theory. It's like, is it pointing at each other? That's kind of it. And I'm glad it feels like a duh, but at the same time, it's like, if things aren't aligned, you have no chemistry, okay? So I'll draw it this way. Okay. so many arrows flying around, right? This is like a reaction arrow before and after. And that's like a momentum arrow. Okay, so many arrows. All right, once you finish drawing that second one, tell me what you think of it. Okay, I got a head nod. All right. In this picture, we need the F and the H to stick the landing, right? The only way that happens is if they literally collide. Do we have H and F colliding here? Yeah, and here certainly not. Okay, so this is happy, this is fail. Okay. And if we're to draw things in the same spatial orientation as here, C, L, H, F in that order, then we would end up with a picture like that. Okay, fluorine comes with sufficient speed, sufficient energy to whack that hydrogen off, and then it sticks to the fluorine. All right. That's the second part of collision theory, alignment. It's kind of that simple. All right. So if we go back to our gas simulation, if we had HCl's bouncing around with F's, you would have no reaction occur if those two bounce. They would just bounce back off. Okay. But if the fluorine came into the hydrogen side, then you'd see a switch of bonding partners. Okay. So basically, if you really think about it, the only way this reaction goes, I had a drawing. Yeah. If fluorine is coming in anywhere from the H side, okay, this works. Anywhere from that side, okay? Of course, the more head-on a collision, the better, okay? The more head-on the collision is, the less incoming speed you need, okay? But if you're coming in from the side or something, okay, with sufficient speed, it'll be all right, okay? But this side, if you're coming in from the other side, this doesn't work, okay? So you can kind of think of hot zones versus cold zones. No pun related with temperature, but for making a reaction work. Where can we do chemistry? Where can't we? Yeah.
So the first one you did, it doesn't go into the HF plus C1? Like that's wrong?
Yeah, this won't work.
Okay.
Yeah, because the F and the Cl aren't isn't the product of interest. Okay. Now, for some reactions in Chem 101, we're just going to keep the reactions very simple, where only like one product of interest is possible. Okay. You go deeper into chemistry. What if this bond was undesirable, but still possible? Then you get side products. Okay. And that's a whole nother level of chemistry. I mean, if you make side products, then you have to figure out a way to separate the good from the bad. And then suddenly you can see why it's its own career. Okay, because most people don't feel like dealing with that, right? You just say, oh, I got a junky mess. Chemist, separate. Okay. All right. So good versus bad. All right. Let's do maybe another example. Let's do. And I'm drawing everything with correct Lewis structures, which is not critical for understanding how to do this. That's good practice for exam 2. Okay. So the reaction on paper is carbon monoxide plus oxygen gives us carbon dioxide. Okay. This is an important reaction for public health purposes. This is what your catalytic, bless you, this is what your catalytic converter does. Okay. We don't want to be breathing carbon monoxide. It's poisonous. All right. So your catalytic converter will pull an oxygen from the air and slap an extra one onto the carbon to have the less dangerous carbon dioxide. Okay. Then while you're working that one, we'll make some water. Okay. And I know water in reality, you're working with H2 and O2 instead of H and O individual atoms. But to simplify our analysis, I'm just going to pretend we have synchronous. Okay. Please, some of you find this chemistry a little funner to think about than all the math and stuff. Just today we learned to make things point the right way. I think that's not too bad. Oh, yeah.
No, third one, is there supposed to be an O in front of the first stage?
Which line?
That one, it's supposed to be OH plus O.
H plus O, you get HO. We're just slapping these two together. Yeah. And then for step 2, we're going to add a second hydrogen. And we're going to consider whether this one makes water or that one makes water. Hey. Quick show of hands. Yeah, Michael.
So in a displacement reaction, you have to break one bond to make the second one, right? Would making that second one release the same amount of energy that breaking the first one takes?
This one versus the earlier example.
Or like anyone in general? just
Yeah.
like trying to connect this to like the conservation of
Yeah.
energy.
Yeah. So this one would require some sort of input of energy. Every reaction requires an input of energy and will release some energy. Okay. If the resulting bonds are stronger than the previous bonds, you'll have more energy released. Okay. Compared to what was coming in. Okay. So is this we call that endothermic versus exothermic, okay, which was going to be more of a Friday thing, but I'll introduce it right now. generally speaking, making bonds with oxygen is exothermic because it is such a good bond. You're going to have an overall release of energy. And basically, if you don't release that energy, you're thinking about conservation momentum. Okay, this oxygen comes in, it can't stick the landing unless it releases some energy, because otherwise it just bounces back off. So as it collides, some other thing has to come in and absorb some of that collision energy so that the oxygen momentum is slowed down and sticks to the landing. Otherwise, it just bounces back off elastically. Okay. You've taken physics, right?
I'm taking it.
Taking it, okay. If there's a little bit too much physicsy language in there, I knew Michael had taken physics, but basically, that'll be.
That makes sense, thank you.
Yeah, you betcha. That's explored way more in Chem 111. Yeah.
I might take
Yeah.
it.
What's that?
Might take it.
Nice, nice. Okay. All right, top or bottom for carbon monoxide? Okay. Yeah, because the top one, we'd end up with cuckoo, okay, we go like that, and that is not that, right? We need OCO, we don't need CO. Yeah, and then for the water mechanism, okay, for the second step, it'd be the first option mentioned, okay? So hopefully you can see with the water formation, the first hydrogen step is really easy because we have 360 degrees and a front and back. We have all three-dimensional space for collision, okay? So this is virtually instantaneous. The second one, though, you only have half of the available volume of space in order to get that second hydrogen added. Okay. So hopefully you kind of feel these things in 3D space without even necessarily busting out any math, okay? And chemistry is a 3D subject at times. Okay. All right. Questions? Okay. No one asked me about the catalytic converter, so I'm not going to go there. Why is a catalytic converter needed? That's for another day. Okay, good. All right, that's kind of part one of today. All right, part two of today is now that we've thought about collisions, we will actually need to put into action the measurement of the strength of the collisions. AKA, we need to know something about temperature. Okay, so for the remaining part of this week, okay, remaining part of today, as well as all of Friday, we're going to be thinking particularly about temperature. Okay, I know collision theory involves pressure, volume, and temperature, and a number of gas particles or solution particles, whatever you're working in, but we're going to hone in mostly on temperature for Hemira. Okay. All right, so we're going to turn our attention to this scary looking word, calorimetry. And I know when I first saw this word, even for someone who liked chemistry, when I first saw this word, I wanted to run away. Okay, had a lot of syllables, like, oh my gosh. And then calor, it reminds me of the Spanish word of dolor, I think is a word for pain or something. So I always had that weird association, but calor means heat, okay? And metry means measure of. So it's actually not as bad a word as it appears. The measure of heat. How do we measure heat? Okay. And if we can measure heat, we can learn a lot about a reaction, or even not just chemistry, some things, physical properties as well, okay? Such as specific heat capacity, the property you're studying this week in lab. Okay, so we need a way of measuring heat. Okay, if you want 98+% good results, you're going to spend hundreds, maybe thousands of dollars on a calorimeter. Okay. And a calorimeter you got stainless steel walls, and this is vacuumed out. So you have vacuumed insulated vacuum, okay, vacuum insulation, okay. And then you screw on a lid real tight, okay. And you have no heat loss to environment, heat loss / exchange with environment. Okay. And it's impossible to entirely prevent heat loss, so I'm gonna put no in quotes. Okay. But you can minimize it, okay? And $1,000 on a calorimeter, okay, all these nice fittings and stuff, the best O-rings and whatever, you're going to have a way of measuring how much heat is released or absorbed in a reaction or a process without interference with the outside environment, okay? But in lab this week, we're gonna go for the less than $10 option, okay? And you'll have, roughly speaking, 90%, maybe even better for some of you, depending how fast you are with your hands, 90% good data with coffee cups. Okay. You can build a calorimeter with coffee cups, okay? As you're going through your lab this week, it's gonna keep saying calorimeter. Like, what do they mean by that? We're just talking about the coffee cups. Okay. So in lab, and like seriously, like coffee cups, as cheap as they are, okay. You have 2 coffee cups. That's what you're gonna do in lab. Maybe have a third. We'll even use a beaker for extra insulation and just so frankly it doesn't fall over from the weight of the temperature probe. And then you're just gonna put a lid on it. Okay. So it's all styrofoam. Okay, the coffee cups are styrofoam. And styrofoam is a type of plastic called polystyrene that's been injected with air, okay, or nitrogen. Air is cheaper, okay, and that's how you get that like bubbly, foamy material. Okay, the lid is also polystyrene, but instead of injecting air into it, they just keep it the normal plastic. So that's why it's like thin and normal looking as far as plastic goes. Okay. And polystyrene, the nature of the molecule itself, as well as if you inject air into it, that gives really good resistance to the loss of heat. Of course, it's not perfect, but it's definitely going to be better than many other materials. Okay, so coffee cups. Okay, second lowest tuition, we're going to use coffee cups. Okay. Yeah. Oh, by the way, if you poke your, this happened earlier, if you poke your probe through the coffee cups this week, you're gonna leak all the water. Ask for some, all right? Good. Not a big deal. Okay, so we gotta measure heat in a calorimeter, okay? So before we talk about how to do the calculations, we have to talk about what heat is in the first place. Are we ready? So what is heat? Okay, I think the best way to explain what is heat is to also explain what isn't heat, okay? And more specifically, I want us to talk about heat versus temperature. Really closely related subjects and often used as synonyms. And for some of life, it's okay to use them as synonyms. But if you want to really understand things technically, you're going to have to understand they don't mean the same thing, technically speaking. Okay. All right. So before you write the definitions, let's come up with an analogy. All right. Swimming pool versus a matchstick. Who's heard of this one? Oh, okay. Swimming pool versus matchstick. So we can put out the pencil for a moment. What's hotter? A matchstick, a light on fire versus the swimming pool. Don't overthink this. What's hotter? The match, okay? Which one burns you? Which one's owie? Okay, the match, okay? I guess a swimming pool on a cold day is owie because it's so cold, but you're not destroying your skin cells. But anyways, okay? The matchstick has a higher temperature than the pool, okay? Now you're probably detecting an incoming paradox, and you're right. Here's my next question. Which has more heat? The little itty bitty matchstick on fire versus the Olympic size swimming? Because I set up a paradox. But then you're like, okay, so I know you set up a paradox, but why is that really the answer? So yes, the swimming pool has more heat than a matchstick, and we're talking millions of times more. Heat is a measure of the collection of vibrational energies, okay? Heat is plainly speaking, it's the amount of vibrations you have, okay? The more vibrations you have, the more heat, okay? When you heat up something, I heat up my water when I make tea, you have all these water molecules, okay? What's happening to water molecules? More heat, more movement. You have water molecules bouncing, you have water molecules rotating, you have water molecules vibrating. Wait, what? Vibrating molecules? That seems like complete nonsense. Josh, you are making things up. I am leaving right now and getting a tuition refund. All right, let me explain. Okay. So we talk about water. I'm gonna write this under temperature. Here's a water molecule. And we're gonna draw this thousands of times this semester. If you jack up the temperature, you can have up, down, I said that backwards, left, right, forward, backwards, movements. Okay. By movement, I'm not talking about just any type of movement. Here, I'm referring specifically to like going from point A to point B. Okay. And a stronger movement means a faster movement. Okay, this is slow, this is fast, bless you. Okay. These A to B movements have a physics or chemistry word for it, and they're called translations. Okay, it has nothing to deal with Japanese to English. It has nothing to deal with Tom Hanks movies. Okay, translations A to B. Okay, so that is one type of movement that you're going to make faster and stronger when you jack up the temperature. Okay, translations. Okay, the next type of movement is going to be vibrations. Okay, so with water, okay, we talked earlier about how a bond is like a spring. Wait, what? I don't remember talking about that. Well, let me refresh your memory. Between the hydrogen and oxygen, if I pull it apart, the positively charged center of the atoms, the nuclei, will get more, they'll want to get restored to the electrons pulling them in, okay? And you press on those electrons too much, then the positively charged nuclei, as well as the electrons, are repelling and we go back out. So you get the spring-like action. The hotter the temperature, the more you have these stretches going back and forth, okay? Your molecule is going to be jiggling more, okay? As some people call it. Yeah, I like the word vibrate over jiggle, okay? Jiggle reminds me of, I don't know, Jello or something. And then I have my old 5-year-old nightmares of the Jello coming alive and stuff. So I avoid that word, okay? But vibrations, okay? So you have more boom, 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 okay? You walk into advanced chemistry or physics classes in a test, you'll sometimes people go like this. They'll like calculate the infrared and Raman spectrum of water, how it interacts with infrared light. And then it's all based on the vibrations. You'll see people do an exam, they'll be like, and then they'll be like, and it's like really dorky. And then we're like, because water can wag, right? And then they'll be like, no, that's rotation. You can't go that and that way at the same time. You're rotating at that point. Okay. Which leads to my next one, rotations. Okay. We're thinking about all the different ways you can move molecules. Okay. What if you make a bond vibrate so hard that the bond breaks? Then the bond breaks. Okay, that's how you do chemistry. Okay, you break them bonds. Okay, how about when you're heating water in a microwave or microwaving food? The microwaves rotate the molecules, and you have rotating molecules bumping to each other. They're going to cause vibrations as well. Okay, so that's how your microwave works. Okay. Microwaves rotate the water molecules, which turns into vibration. Okay. So this is what's describing temperature. And a higher temperature means more movements. Okay. And it means stronger movements. So with that said, now we can define heat versus temperature. Put this up. What is heat? Heat is the total amount of movements. Okay. Heat is the total amount of movements. Okay. And you want to get really pedantic, if you've taken a physics class, I should be referring to thermal energy. Heat, the technical definition is the amount of thermal energy transferred between two or more different bodies. Okay. Most chemists roll their eyes when you have to give the physics-based definitions. Okay. Most chemists just use heat versus thermal energy synonymously. All right. Whereas temperature, what is temp? Temp is I'll put average in small parentheses. I'll forget that. It's the strength of the movements. Okay. Keyword being strength. So that's why the matchstick had a higher temperature. Okay. Those molecules are moving way faster, way stronger in the matchstick compared to the water in the Olympic-sized swimming pool. Okay. But the swimming pool has more vibrations overall going on than a little matchstick. Okay. We talked about intensive versus extensive properties early on in the semester. We talked about how some things change regardless of, some things don't change regardless of the size, okay? Temperature is an intensive property because no matter how much of something you have, the temperature is still just a temperature, okay? Whereas for heat, the more of something you have, the more heat exists. Okay, so this is extensive. Okay. I don't plan on putting extensive versus intensive into like an exam necessarily, but I did sneak that into a homework question. Okay. Okay, temperature is not dictated by size, but the amount of heat is. Bigger substance, more heat. Kind of that simple. Okay. All right. So that's our crash course on heat versus temperature. We'll talk about the units and then we'll begin calculations. And which will help with lab a lot. All right. I'll pause here for questions. Hopefully we're hanging tight here and I'm making somewhat sense. Okay, maybe. All right, cool. All right. We're getting closer to the calorimetry equation. Let's talk about heat units and then we'll be set. We have J for joules. We have KJ for kilojoules. And joules can be upper or lowercase. For the word, for the unit, it's a capital J though. And that's a lowercase k in front. It's kilo. And then we have the other main energy unit of chemistry, which is calories. And then we have a lot of calories. We might want to do kilocalories instead. Okay. What's the difference between these units? They're basically equal. It's a matter of preference. I feel like for a lot of water-based work, people will prefer the calorie, and there's a good reason for that. The calorie unit was designed with water in mind, okay? I'd say other areas of chemistry or physics use joules more often, but when it comes to calorimetry, I feel like the calorie is a little bit more popular, okay? But since both are commonly used, you'll need to be able to convert between them. And there's the conversion factor. I will provide that on an exam 3. There's no need to memorize if you don't want to. Okay, but 4.184 joules is 1 calorie exactly. Okay. All right. Now, one more note, and then we'll be ready to do some example problems. And then I'm going to pull them straight from the homework, actually. Yay. I don't know if this is a rant or an explanation. I guess it's both. A kilocalorie is also known as a capital C calorie. Okay. I'm not going to put that on test. This makes me a little bit upset. Okay. Because a lowercase c to me looks the same as a capital C. If your handwriting is bad like mine, especially. Okay. Where do you have to care about this? A handful of you will have to take or have already taken a nutrition class. Okay. And when it comes to nutrition in America, okay, to determine the calorie content of food, we put it in a calorimeter, we burn up the food, and then we see how much hotter the water got as a result of burning up the food, okay? So that's how we measure calories for food. We literally burn it, okay? We don't do this for 101 lab anymore, but we used to like burn a Cheeto or something and you figure out how much calories was in the Cheeto, okay? On nutrition facts, they write calories with a capital C, but that's the same as a kilocalorie, okay? So FYI, okay? In nutrition class, or you read a nutrition facts label on your food, they're talking about kilocalories, okay? Don't get me wrong, I love America, but some countries, okay, they'll say kcals on the label instead of capital C calories. And I applaud that. Okay. Anyways, little rant / explanation. Okay. All right. So there's a few homework problems to get you warmed up on these conversions. I'm not gonna do examples of that. We've converted a jillion things at this point. So I think we're ready to just launch into the calorimetry calculations. Okay. I think I'll probably want to start a new page. Okay, so the way we're going to explain this could work for a variety of processes, but we're going to do just a classic heat transfer experiment. This is the same one you're doing in lab this week, okay? So we're going to do a heat transfer experiment. Okay. And we're going to write some equations shortly. These will be provided on an exam 3, so don't fret too much. In a heat transfer experiment, your goal is to calculate the specific heat capacity. I know that's a mouthful. Okay. And that's gonna get a letter C. Most people will have that C a lowercase. Okay. We're gonna calculate something called the specific heat capacity of an unknown material. Okay. And that'll be to help identify it. All right, so that's our goal, and that's the goal in lab this week as well. Okay, we got to figure out some property of matter, okay, called specific heat capacity. What on earth does that mean? Okay, I'll explain in a moment. That's a goal in the heat transfer experiment. Okay. Specific heat capacity, I think I usually just call it specific heat or heat capacity. Technically, heat capacity versus specific heat capacity mean two different things. For one-on-one students, you don't have to care about that, okay? So in one-on-one, I just use all those different terms interchangeably and we don't care, okay? So we have to talk about the units of specific heat. Okay, C. You're gonna have calories over grams times degrees Celsius, or you're going to have joules over grams times degrees Celsius. 3 units, oof. 3 units, man, I like back in the day when things only had 1 unit. No, we need 3 units here. I'll try to make sense of it for you. All right. So those are the units of C for heat capacity. Once you got that written down, we're going to try to make sense of this. All right. Let's talk about the first unit, calories or joules. Okay. Those are measures of heat energy. Okay. So you give something more calories, it's going to be heated up more. Okay. Then we have grams, and then we have degrees Celsius. Okay. So my nickname for this is heat ability for specific heat. Heatability. How easy is it to heat up something? How hard is it to heat up something? That's what I mean by heatability. Okay, and that's exactly what specific heat tells you. Okay, it's very useful. Okay, it's a very useful property. It applies a lot to cooking. Okay, everyone knows I like to talk about food, right? So there's the old adage, idiom, it takes forever to a watched pot to boil, right? It takes forever. Okay. What does that say about heat ability of water? It's difficult to heat up, okay? So put in plain language, water has a high C. I'm not talking about the drink. I could use some of that right now, okay? Water has a high specific heat, okay? It's hard to heat up, okay? Hard to heat up water. In fact, the specific heat of water you need 1 calorie let me get that all written before I talk. The C of H2O is 1. I wrote 1.00, but it's exactly 1. It's exactly 1. So infinite sig figs. How can you have a substance where it's perfectly 1? That's because the calorie was made for water. Let me explain. See, on the previous page, I'll put this back up in a moment. On the previous page, we said 4.184 joules is 1 calorie, okay? So at one point in time, water specific heat was measured as 4.184 joules per gram degree Celsius, okay? Someone eventually had the thought, I'm tired of writing 4.184 if we're dealing with water all the time. Let's just call that 1 calorie. That's gonna make life way easier. And instead of writing 4.184, we'll just say it's 1 calorie, okay? So calorie was designed with water in mind, just like Celsius was designed with water, okay? So that water's high specific heat, okay? Most molecular substances, okay, woods, rubbers, plastics are gonna have, there's some exceptions. Plastics, it depends on the plastic. They're gonna be harder to heat up, okay? How about metals? Metals almost always have low specific heats. Metals are way easier to heat up, okay? I have a north-facing house, okay? In the morning, my car is in the shadow, okay? Hood is frosted over, okay? And these days, by the time I'm done with work and go to the parking lot, the hood's on the hotter side, unless I'm working late, okay? Which is just my point. The metal, you can get up and down easily, okay? What are some metals that come to mind? Well, we'll write down a few examples. Steel. Okay, steel is about 0.1 calories per gram degree Celsius. You said copper. 0.09 about the same as steel, a little bit lower. But look, we're talking 1/10. Okay, it takes 10 times less energy to heat up steel or copper, and that's why they get hotter, okay, a lot faster. How about something like aluminum? About 0.2, 21345, depending on where you look, okay? About 0.2. So aluminum takes about twice the amount of heat to heat up compared to steel, okay? Well, that sucks. Actually, that could be a good thing, okay? I'm a little bit of a cooking nerd at times, although I've definitely become a lazier cook over the years. But a few years ago, I treated myself for a birthday or Christmas or something. I bought an expensive stainless steel pan, okay? What's so good about stainless steel is normally cheap, right? Well, the interior of the pan is not stainless steel, but it's aluminum, okay? Because the interior is aluminum, it takes longer to heat up, but that means it's going to hold its heat longer, okay? And you have the property of steel on the outside, which gets hot easily. So basically the aluminum core, okay, it's made by T-Fall. No, I don't get paid to say any of this, but okay, that's not a pan. It's kind of like that, and then it has an aluminum core, okay? And it becomes a reservoir of heat, okay? It takes longer to heat up that aluminum core, but then the stainless steel, okay, is fed the heat from the aluminum, and thus you're able to maintain a hot searing temperature for a longer time, which means steaks come out good and the family's happy, right? And me, all right? Maybe not my heart, but, okay? So that's to deal with specific heat. All right, we will learn how to calculate this next class. All right. If you don't want to wait until next class to learn, you're free to look at the calorimetry video on my channel. Otherwise, that's where we're going to be going over starting Friday. Again, exam will open tomorrow, and if you got here late, I'll say this in an email, but I decided the exam 2 study guide or practice exam, just the way it is, will be your exam. I'm not adding any gram to mole stuff because I'm extending that homework. All righty, thanks and take care.
Okay.
Thank you.
Well, the drafts.
Something like that. Yeah, I got a lot of cries for help in the email, so I don't want everyone to flunk. So let's make these stuff.